Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. We are continuing with structural biology techniques. We have talked about X-ray, we have talked about NMR. These are, as we have discussed, the two high resolution techniques to solve protein structures. Today we are going to start a module where we will talk about cryo-electron microscopy, another high resolution technique. So, cryo-electron microscopy, as you see the entire setup of the instrument, we will talk about that in details. Cryo-electron microscopy or cryogenic electron microscopy, or in short it is a cryo-EM, is an electron microscopy technique applied on samples cooled to cryogenic temperatures and embedded in an environment of vitreous water. So, look at the terms here. This is a microscopy, this is a electron microscopy. So, the source is electron and applied on the samples which are cooled to cryogenic temperature and embedded in an environment of vitreous water. So, I would say 4 words. 1, first is microscopy, this is a microscopy. Second is this is electron microscopy, then cryogenic temperature is used and vitreous water. So, we will know about all of them. An aqueous sample solution is applied to a grid mesh and plunge frozen in liquid ethane or a mixture of liquid ethane and propane. So, an aqueous sample, here we are using. So, if you remember, we will continuously compare NMR, X-ray and cryo. Both NMR and cryo, we are applying aqueous sample. So, aqueous sample solution applied to a grid mesh. So, you need a grid mesh where it is kind of immobilized and plunge frozen in liquid ethane. What is plunge frozen? We will look at, while liquid ethane we will look at, or a mixture of liquid ethane and propane, we will look at them. While development of the technique began in the 1970s, recent advances in detector technology and software algorithms have allowed for the determination of biomolecular structures at near atomic resolution. If you remember, NMR around, I would say 3 to 4, X-ray 1 to 3 angstrom, cryo started with 70 angstrom or even more, and now the latest structures are even less than 2 angstrom. We will talk about the journey of cryo-EM as a technique, a great journey we will talk about. Continuing with the information about cryo-electron microscopy, this had attracted wide attention to the approach as an alternative to X-ray crystallography or NMR spectroscopy, as I talked about, for macromolecular structure determination, and one of the biggest thing is you do not need a crystal. In 2017, the Nobel Prize in Chemistry was awarded to Jacques Dubochet, Joachim Frank and Richard Henderson for developing cryo-electron microscopy for the high resolution structure determination of biomolecules in solution. This is Dubochet, this is Joachim Frank, and this is Richard Henderson. Also, Nature Methods also named cryo-EM as the method of the year in the year 2016. So, basic questions are there. So, we talked about microscopy, but people who are newcomer, who are just beginner, for them what is microscopy and how microscopy works, history of microscopy a little bit, how it developed, how from starting with the light microscope coming to the electron microscope, what are the electron microscope, how that goes to the cryo-electron microscope. We will talk about simple and compound microscope, types of microscope. As I say electron microscope because cryo-electron microscope is definitely an electron microscope, transmission and scanning electron microscope, all of these we will discuss today. To start with, from where the need of microscope comes, if you see what we could observe, we look to the outer limits of the universe, right, this is the universe. We look at microbes, bacteria, we look at viruses, this is the viruses, you guys now know this because you all know about COVID-19. We look at chromosomes, so some of them take the limits of our what we could see in the normal eye. So, normal eye could not see the objects less than 100 micrometer in diameter. So, it is the limit of the normal eye. The size of bacteria varies from 1 to 5 micrometer. So, in this moment you are listening to me, in that time a few bacteria is going where you are sitting, through your hands, everywhere, and you could not even see them in normal eye. The size of viruses ranges from 25 to 350 nanometer, even smaller. The hand lenses provide us the enlargement of 2 to 10x. What I mean by this? I mean by this, you make a lens and the lens is a tool which would enlarge the power of eye. The lens is helping you to magnify, enlargement of the object. This is the basic concept of microscope, something which helps your eye to see by making enlargement of that object which is not in the limit of your eye. You will say that that is a basic microscope. So, technically they are the simplest microscope. I hope you understand. Your eye could see around 100 micrometer in diameter. If you have to see something less than that or something far away, you will take help of a lens, and that is called the simplest microscope. So, the simple microscope is a tool which help magnifying or enlarging an object so that it could come in the limit of your normal eye visibility. So, light microscope by definition, the optical microscope often referred to as light microscope is a type of microscope which uses visible light and a system of lenses to magnify images of small samples. So, what started with one lens, now people have make a little complicated system with different lenses. Let us take a look. So, simple microscope, you have your eye, you have lens, you have the object and the image is enlarged, what we already talked about. So, a simple microscope is a microscope that uses a lens or set of lenses to enlarge an object through angular magnification alone, giving the viewer an erect enlarged virtual image. The use of a single convex lens or group of lenses are still found in simple magnification devices such as the magnifying glass and eyepieces for telescopes and microscopes. So, this is simple microscope. Now, compound microscope. A compound microscope is a microscope which uses a lens close to the object being viewed to collect light, which focuses a real image of the object inside the microscope. So, there is one lens and there is another lens, eyepiece lens and objective lens. So, you have first the image 1 created and then enlarged image 2. So, object it goes there, a enlarged image 1, then it further enlarged in the image 2. So, you use a combination of a eyepiece lens and an objective lens. So, that image is then magnified by a second lens or group of lenses that gives the viewer an enlarged virtual image of the object. So, this is the objective lens creating image 1 and this is the eyepiece lens creating the further enlarged object. Now, here the compound microscope, this is a basic representation of a compound microscope. You put a series of lenses, it becomes a real microscope. What is about objective lens? Role to gather light rays coming from any point of the object. You have the object, the function of the objective lens is to gather light rays coming from any point of the object to unite the light in a point of image. So, it goes and to unite it in the point of image and to magnify from this one to that one, a magnification definitely happen. This magnification is the function of the objective lenses. Basic we have studied them in our 10th 12th level. Now, what is aberration? There are two type of aberration. One is spherical aberration. Light rays hitting periphery will be more refracted than the rays hitting center or lens, and there is chromatic aberration. White light of passing through simple lens, each wavelength will be refracted to different extent. So, one is if you have the lens, the diffraction here and at the edge would be different. Light rays hitting periphery will be more refracted, they will be refracted more than the middle or any other places, and chromatic aberration is white light of passing through simple lens, each wavelength would be refracted to different extent. As we know about Vibgyor, blue brought to a shorter focus than red result in an unsharp image of the color fringes. So, objective lens, there are three type of objective lenses: achromatic, which is simplest in construction and adequate for most of the purposes. Fluorite, aberrations are largely removed by this type of objectives. Apochromatic, most corrected in terms of aberration. So, we have two type of aberrations and the aberrations are corrected by getting different objective lenses. Eyepiece lenses role to magnify the real image to the object from the objective lens and to correct the defects of the objective. So, it take to magnify. So, this is the real object, it come to image 1. So, the role of eyepiece lens is take the image 1 and enlarge it 1, correct the defects of the objective lens. What is the usefulness of a compound microscope? The use of a compound objective and eyepiece combination allows for much higher magnification, as I talked about, it also helps in removing the aberrations. In an optical microscope, the functionality is depending on the resolving power, numerical aperture and obviously magnification. So, what is the resolving power? The power of an objective able to separate distinctly two adjacent points. Two adjacent points are very close. So, you use a lens and you could not separate, and you use a lens you could separate, that is the resolving power. So, the resolving power depends on wavelength of the light used, numerical aperture of the lens. Larger numerical aperture means greater resolving power of the objective and finer detail could be studied. We will come to resolving power when we also make a transition from a light microscope to the electron microscope. The features for resolving power, it is the ability to differentiate two close points as separate. The resolving power of human eye is 0.25 millimeter. The light microscope can separate dots that are 0.25 micrometer apart. The electron microscope can separate dots that are 0.5 nanometer apart. So, now you would understand the difference between a light microscope and an electron microscope, but why? Why when you compare, why electron microscope is having so high resolving power? We will take a look in our further analysis. So, numerical aperture NA, the numerical aperture of a lens is the ratio of the diameter of the lens to its focal length. So, if you see, this is the focal length from the point the object to the lens, and numerical aperture can be decreased by decreasing the amount of light that passes through the lens. So, this is the diameter of the lens and focal length, that is called numerical aperture. Numerical aperture is a dimensionless number that characterizes the range of angles over which the system can accept or emit light. It is the acceptance cone of an objective and hence its light gathering ability and resolution. N a numerical aperture equal to n sin theta, where n is the index of refraction of the medium in which the lens is working and theta is the half angle of the maximum cone of light that can enter or exit the lens. So, here if you see, the numerical aperture with respect to a point P depends on the half angle, this theta of the maximum cone of the light that can enter or exit the lens. Coming to magnification, magnification is the process of enlarging something only in appearance and not in physical size. This enlargement is quantified by a calculated number also called magnification. A microscope which makes a small object appear as a much larger object at a comfortable distance for viewing. A microscope is similar in layout to a telescope, except that the object being viewed is close to the objective, which is usually much smaller than the eyepiece. So, that is the only difference between a microscope and a telescope. Coming to another thing which is called condensers. The condensers could be defined as a series of lenses for the illumination of the object under examination. Several methods are employed for illustrating the object under examination. In microbiology, we have two methods commonly employed. One, illumination by transmitted light and dark field illumination. We will talk about them. So, bright field microscopy. The ordinary microscope is called as a bright field microscope. It forms dark image against the bright background. So, normally it is the bright background and it form a dark image. The useful magnification of light microscope is limited by its resolving power. The resolving power is limited by wavelength of illuminating beam. Resolution is determined by certain physical parameters like wavelength of light and light generating power of the objective and condenser lenses. Higher numerical aperture, better light generation, better resolution, shorter the wavelength, better the resolution. So, bright field microscope you see here bacilli and cocci, they are shown under light microscope, that is called bright field microscope, where the background is bright and the picture, the image is dark. This is paramecium specimen again in bright field or common microscope. What is dark field microscope? The dark field microscope, it is creating an image with a background being dark and picture is illuminated. So, a bright field microscope can be adapted as a dark field microscope by adding a special disc called a stop to the condenser. The stop blocks all light from entering the objective lens except the peripheral light that is reflected off the side of the specimen itself. The resulting image is a brightly illuminated specimen surrounded by a dark field. So, these are the images created from dark field microscope. You see the background is dark and we see here paramecium, Volvox pyrogyra, Treponema vincenti. So, all of them are bright and the background is dark, that is called dark field microscope. There are different types of microscope. One could group based on what interacts with the sample to generate the image. So, lights or photons, when they are interacting, it is called optical microscope or light microscope. When it is electron, it is called electron microscope. When they are having a probe, they have to scan, they have a width x, y, then they have a z axis. So, you get to know the depth. So, use a scanning probe, that is called scanning probe microscope. And you could also group whether they analyze the sample by a scanning point like confocal optical microscopes, scanning electron microscope and scanning probe microscopes. Analyze the sample all at once, wide field optical microscope and transmission electron microscope. So, these are different type of microscopes. Now, we are coming to electron microscope. I hope you have already remember that cryo electron microscope is an electron microscope. So, now what we see the simple concept of a light microscope, now we will come to the electron microscope, why we need electron microscope and all these things, because now I hope you have an idea about what is a microscope, how microscope generally take the light ray and make it a enlarged image, a simple thing. There is a lens, the lens magnify. So, there are two type of lenses, objective lens and eyepiece lens. There are series of them, series of eyepiece lens, series of objective lens. Now, coming to electron microscope. Electron microscope was invented because of the drawback of the light microscope. We have already talked about the drawback. The drawback is, it is about the resolving power. Lights passing through slits get diffracted. The convex lens collects the diffracted light. After collection, it produces image of the slit on the screen. So, light passing through the slit get diffracted. The convex lens collect the diffracted light. After collection, it produce image. So, from the slit it comes the diffracted light. The diffracted light is collected by the convex lens and it goes and makes the image in the screen. Edge of the slit used to diffract the light. To see the edge clearly as an image, the lenses must collect the diffracted light. So, you have the lens and the lens have to collect all the diffracted light, right. If the light pass through here, this is not collected. So, when it creates the image will be blur because it is losing the information here. With the width of the slit decrease. So, you have a width like this, now you get this. More decreased the slit, the diffraction would be increased. So, if it is a big one, it is like coming here, small it goes here. Now, the objection of the lens failed to collect the diffracted pattern. It cannot collect all the diffractions. As a result, blur images would be developed. So, the SERP image is created when all the diffracted rays are collected by the lens. When the slit is getting reduced, the reduced slit increased diffraction, unable to collect. So, information missing, resulting blur image. That is the problem. So, again going back about what we discussed, resolving power D, which is lambda by 2 Na. Na is the numerical aperture. This applies when Na of the condenser lens is equal to or greater than the objective's nuclear aperture. Also, when the illumination consists of nearly parallel rays form into a cone of light whose angle matches the objective lens's angular aperture. So, we are talking about Na, the numerical aperture. So, the resolving power we have already discussed, it depends on the wavelength of the light used, the light we are using and the numerical aperture of the lens. Resolving power depends on wavelength of the light used and the numerical aperture. So, we talked about the resolving power depends on the wavelength of the light used. Now, if you see, this is the electromagnetic spectrum. You see here, it is from the radio waves to the cosmic rays, where the wavelength is decreased. If you look at this, this is the visible region where we could see in normal eye. You will see that the red have the highest wavelength and blue have the lowest. What will happen here? Red light, as we say, long wavelength, 750 nanometer wavelength. So, when the wavelength is long, more diffraction and less resolution. Whereas, in case of blue light, short wavelength, 380 nanometer wavelength, less diffraction, more resolution. This is a very important slide. Coming to de Broglie equation, before that I would talk about de Broglie. I hope you all know about de Broglie. Louis Victor Pierre Raymond de Broglie, he was a French physicist and aristocrat who made groundbreaking contribution to quantum theory. And when I say groundbreaking contribution, you would be surprised to know that this groundbreaking contribution was made while doing his doctoral studies. In his 1924 PhD thesis, he postulated the wave nature of electrons and suggested that all matter has wave properties. So, why I call de Broglie here? The de Broglie equation is an equation used to describe the wave properties of matter, specifically the wave nature of the electron, which is lambda equal to h by mv, where lambda you know the wavelength, h is the Planck's constant, m is the mass and v is the velocity. So, where lambda is wavelength, h is Planck's constant, m is the mass of the particle moving at a velocity v, de Broglie suggested that particle can exhibit properties of wave. You remember, if you go into that background, there was lot of controversies going through because people are jumping about the wave particle duality. Some were for wave properties, some were for the particle property, the classic science. The de Broglie hypothesis was verified when matter waves were observed in George Paget Thomson's cathode ray diffraction. Cathode ray diffraction, why it is very important? This is the kind of birth of electron and their existence, and talking about that, and the Davison-Jarmar experiment, which specifically applied to electrons. And since then the de Broglie equation has been shown to apply to elementary particles, neutral atoms and molecules. So, let us take lambda equal to h by mv. So, the wavelength is proportional to mass. What is the mass of electron? See here, 9.1 into 10 to the power minus 31 kilograms. Like electron, proton, neutron, they have their mass. Proton, neutron have much higher mass, we have discussed it in NMR studies, but photon is not having a mass. We used to say that. Now, with the advent of more sophisticated instruments, more sensitive instruments, yes, you could measure the mass of photon, which is not universal like electron, proton and neutron. So, it dependent on the properties of the source. So, we have to help you understand, I have taken the mass of photon from a helium neon laser of 1.15 micron is equal to 4.71 e to the power minus 38 kilograms. This is much lower than the mass of the electron. You could say basically photon have nearly 0 mass. It is easy to comment that whatever source be the origination of photon, its mass is much less than electron. So, there are different sources, the different sources talk about different mass of the photon, but the mass of photon is much less than electron. Okay, that is established. So, wavelength of the electron is much less compared to the photon. So, you could see from here, if mass is inversely proportional, same is lambda. Coming to electron microscope now, an electron microscope is a microscope that uses a beam of accelerated electrons as a source of illumination instead of a light or photon in a light microscope. As the wavelength of an electron can be up to 100,000 times shorter than that of visible light photons, electron microscope have a higher resolving power than light microscope and can reveal the structure of smaller objects. So, we talked about the lambda. If you go back here, long wavelength and less resolution. So, that is coming here. So, long wavelength, less resolution, electron microscope use shaped magnetic fields to form electron optical lens system that are analogous to the glass lenses of an optical light microscope. Electron microscopes are used to investigate the ultrastructure of a wide range of biological and inorganic specimens, including microorganisms, cells, large molecule, biopsy sample, metals and crystals. Industrially, electron microscopes are often used for quality control and failure analysis. Modern electron microscopes produce electron micrographs using specialized digital cameras and frame grabbers to capture the images, making them much more sensitive. So, what is the history of electron microscope? What is the journey? In 1926, Hans Buss developed the first electromagnetic lens, started the journey. According to Denis Gabor, the physicist Leo Szilard tried in 1928 to convince him to build an electron microscope for which he had filed a patent. The first prototype electron microscope capable of 400 power magnification, 400, was developed in 1931 by the physicist Ernst Ruska and the electrical engineer Max Knoll. The apparatus was the first practical demonstration of the principle of electron microscopy. In May of the same year, Reinhold Rudenberg, the scientific director of Siemens, obtained a patent for an electron microscope. Siemens have a huge history as a industry, have a huge history of their connection to the research on electron microscope. In 1932, Ernst Lübke of Siemens and Halske built and obtained images from a prototype electron microscope, applying the concept described in Rudenberg's patent. In the following year, 1933, Ruska built the first electron microscope that exceeded the resolution attainable with an optical microscope. So, up to now, though there is always a potential of the electron microscope to give higher resolution in comparison to the light microscope, the instrumentation setup was not giving them enough opportunity to actually attaining them. But in 1933, Ruska built the first electron microscope that exceeded the resolution attainable with an optical microscope. 4 years later, in 1937, again Siemens financed the work of Ernst Ruska and Bodo von Boris and employed Helmut Ruska, Ernst's brother, to develop application for the microscope, especially with the biological specimens. Also in 1937, Manfred von Adren pioneered the scanning electron microscope. So, as I talked about, scanning electron microscope is nothing but having a probe to scan so that we could get the width. Siemens produced the first commercial electron microscope in 1938. The first North American electron microscope was constructed in 1938 at the University of Toronto by Ellie Franklin Burton and students like Cecil Hall, James Hillier and Albert Prebys. Siemens produced a transmission electron microscope, the TAME, in 1939. Although current transmission electron microscope are capable of 2 million power magnification, as a scientific instrument, they remain based upon Pruska's prototype, only showing how creative, how talented and how big was this innovation. And agreeing to that line, in the Nobel Prize in Physics 1986 was divided and one half awarded to Ernst Ruska for his fundamental work in electron optics, and also for the design of the first electron microscope, the other half jointly to Gerd Binning and Heinrich Rohrer for their design of the scanning tunneling microscope. So, nowadays there are many type of microscopes, but they could be divided into two major types, like originally one is transmission electron microscope or TEM and scanning electron microscope or SEM. Let us take a look on them, what are the differences, what are their construction and all. Coming to transmission electron microscopy, it is the original form of electron microscope. The transmission electron microscope uses a high voltage electron beam to illuminate the specimen and create an image. It uses high voltage electron beam. The electron beam is produced by an electron gun commonly fitted with the tungsten filament cathode as the electron source. We will talk in details when we are going to our topic, the cryo-electron. The electron beam is accelerated by an anode typically at 100 kilovolt, ranging from 40 to 400 kilovolt with respect to the cathode, focused by electrostatic and electromagnetic lenses and transmitted through the specimen, that is in part transparent to electron and in part scatters them out of the beam. So, when electron hit matter, we talked about when light hit matter, when electron hit matter, we also have a lot of effects. When it emerges from the specimen, the electron beam carries information about the structure of the specimen, that is magnified by the objective lens system of the microscope. So, the electron beam carry the information about the structure of the object, that is magnified by the objective lens system of the microscope. So, the setup and all they are same as we have discussed in light microscope, only the source is changed and compatible setup is changed, so that the creation and accommodation is provided. The spatial variation in this image may be viewed by projecting the magnified electron image into a fluorescent viewing screen. The screen usually coated with a phosphor or scintillator material such as zinc sulphide. Alternatively, the image can be photographically recorded by exposing a photographic film or plate directly to the electron beam. So, it could be coated with phosphor or a scintillator material, or it could also be taken in a photographic film or plate. Sometimes a high resolution phosphor may be coupled by means of a lens optical system or a fiber optic light guide to the sensor of the digital camera, that is the kind of modernized version. The image detected by the digital camera may be displayed on a monitor or a computer. The resolution of TEMS is limited primarily by spherical aberration. You remember spherical aberration, as we are talking about, when it is diffracted, the lens is unable to collect it. So, you get blur image. So, your resolution have to be cut off. So, that is the cause of the resolution limit in the TEM. This could be solved by using a new generation of hardware correctors which can reduce spherical aberration to increase the resolution in high resolution transmission electron microscopy, which is called HRTM, high resolution transmission electron microscopy, to below 0.5 angstrom, enabling magnification about 50 million times. The ability of high resolution transmission electron microscope to determine the positions of atoms within material is useful for nanotechnologies research and development. Transmission electron microscopes are often used in electron diffraction mode. The advantages of electron diffraction over X-ray crystallography are that the specimen need not be a single crystal or even a polycrystalline powder. So, all we faced there in X-ray crystallography, you do not have to face it here. Also, the Fourier transform reconstruction of the object's magnified structure occurs physically and thus avoids the need for solving the phase problem faced by the X-ray crystallographers after obtaining their X-ray diffraction patterns. I hope I do not have to go and refresh your knowledge about the big phase problem in X-ray crystallography. We have talked a lot about them. Fortunately, this problem is not present in the electron microscope. One major disadvantage of the transmission electron microscope is the need for extremely thin sectioning of the specimen, typically about 100 nanometer. You have to do the sectioning. Creating these thin sections for biological and material specimen is technically very challenging. Biological tissue specimens are chemically fixed, dehydrated and embedded in a polymer resin to stabilize them sufficiently to allow ultra thin sectioning. Sections of biological specimens, organic polymers and similar materials may require staining with heavy atom levels in order to achieve the required image contrast. Now, we are coming to scanning electron microscope. This is the picture of the scanning electron microscope. A scanning electron microscope or SEM scans the focused electron beam over a surface to create an image. The electrons in the beam interact with the sample, producing various signals that can be used to obtain the information about the surface topography and composition. So, it is talking about the surface, its width and all. The main scanning electron microscope components include the source of electron, which is necessary for all the electron microscopes, column down which electron travels with, so where the electron have to travel, electromagnetic lenses, electron detector, sample chamber and computer and display to view the images. So, this is schematic diagram of a scanning electron microscope. This is the electron gun, this is the source of electron. So, electrons are produced at the top of the column, accelerated down and passed through a combination of lenses and apertures to produce a focused beam of electrons which hits the surface of the sample. So, it comes through and here is the sample. So, it is produced by the electron gun and then come through the condenser lens and apertures and all, and it concentrate and hit the sample. The sample is mounted on a stage in the chamber area, and unless the microscope is designed to operate at low vacuum, both the column and the chamber are evacuated by a combination of pump. So, high vacuum. The level of the vacuum will depend on the design of microscope, but generally high vacuum is used to be used. The position of the electron beam on the sample is controlled by scan coils situated above the objective lens. So, when you see here, we will see the coils present here. This is the objective lens. Okay. These coils allow the beam to be scanned over the surface of the sample. So, these coils, they allow the beam to be scanned over the surface, it rather than hitting it, scan the sample. This beam rastering or scanning, as the name of the microscope suggests, enable information about a defined area on the sample to be collected. So, it will not only take the surface, it also take the width. As a result of the electron sample interaction, a number of signals are produced. These signals are then detected by appropriate detectors. The scanning electron microscope produces images by scanning the sample with a high energy beam of electron. So, this is high energy beam of electron, and it come and hit the surface, and when it hit the surface, there are different effects like fluorescent X-rays, continuum X-rays, characteristic X-rays, backscattered electrons, auger electron, and secondary electrons. As the electrons interact with the sample, they produce secondary electrons, backscattered electron, and characteristic X-rays. These signals are collected by one or more detectors to form images, which are then displayed on the computer screen. So, the electron beam comes, it interacts with the sample, producing different type of rays, secondary electron, backscatter electron, characteristic X-rays. All these signals are collected by the detectors to form images, which are actually displayed on the computer screen. When the electron beam hits the surface of the sample, it penetrates the sample to a depth of a few micron, depending on the accelerating voltage and the density of the sample. Many signals like secondary electrons and X-rays are produced as a result of this interaction inside the sample. The maximum resolution obtained by an scanning electron microscope depends on multiple factors like the electron spot size, interaction volume of the electron beam with the sample. While it cannot provide atomic resolution, some scanning electron microscope can achieve resolution below 1 nanometer. Typically, modern full sized SEMs provide resolution between 1 to 20 nanometer, whereas desktop systems can provide a resolution of 20 nanometer or more. So, what we did in this class, we have started our topic of cryo-electron microscopy, and when we start cryo-electron microscopy, this gives us a lot of basic questions. To answer them, we go to the concept of microscope, we know about what is light microscope and how it start with the concept of observation. Observation makes the limitation of the eye, then the eye limitation would be complemented with a magnification lens being the simplest microscope. Then comes the concept of object lens and eyepiece lens, that brings the concept of compound microscope. The combination of series of object lens and eyepiece lens brings you the modern microscope, but in the modern optical microscope there is a limit, because we know that lambda is inversely proportional to mass and resolution is inversely proportional to lambda. So, it gives us an idea that if we could replace photon by electron, and when we do that, we remember the concept that photon have much less mass in comparison to electron. So, what will happen? The wavelength of electron would be shorter, giving it high resolution. Then we come to the history of development of electron microscope and know a brief about two major class of microscopes, the transmission electron microscope and scanning electron microscope. In the next class, we will talk about the component and functioning of the cryo-electron microscope. With that, thank you very much. As I told you guys, keep listening to the class and keep asking questions. I would be very happy to answer. Thank you very much.